Hi everyone. We're going to talk about fractional composition diagrams in this video. And what you're looking at is a fractional composition diagram for carbonic acid that I made using Excel. And for extra credit, you're going to make a fractional composition diagram of a diprotic weak acid of your choice. You can choose any diprotic weak acid except for carbonic acid because I already did one. But let's, again, just talk a little bit about these diagrams. On the y-axis, I know it's hard to see, but this is the symbol alpha, and it means fraction, or it stands for fraction, and you know what a fraction is. It's just a part over a whole. So we have the fraction of H2A, HA minus, and A minus 2 as a function of pH. And you can see that we have the highest fraction of H2A at acidic pHs, the highest fraction of A minus 2 at basic pHs, and at these intermediate pHs, that's where we have the highest fraction of the intermediate form. So these fractional composition diagrams just show how the fraction of each form changes as a function of pH. So we can write an expression for the fraction of H2A. Again, that's the part over the whole. So the part would be the concentration of H2A, and the whole would be the concentrations of all the different forms in which H2A can exist. So that would be H2A plus HA minus and A minus 2. And you can write similar expressions for the fraction of HA minus and the fraction of A minus 2. Maybe I'll let you do that on your own. So hopefully you got the expressions that I got here. And just to maybe review a little bit, couldn't this denominator be expressed differently? Couldn't we also write this expression for alpha as H2A? What would the sum of all these three different forms have to add up to? The formal concentration. So if I am asking you to create your own fractional composition diagram, you've got to have an equation that relates the fraction, maybe the fraction of H2A, to pH, or at the very least H+. So although those equations for all three forms are given in your Harris text, I do want to take a minute and derive that equation for H2A. So here I've rewritten our equation for the fraction of H2A. Again, that's the part over the whole. And if I'm asking you to make a plot of the fraction of H2A as a function of pH, we've got to get rid of these different variables. We've got to express alpha in terms of H+. And right now, alpha is expressed in terms of three different variables, H2A, HA minus, and A minus 2. So again, we want to express alpha in terms of H+. So looking at this equation, I see H2A upstairs and downstairs. Maybe it would help if I would express HA minus and A minus 2 in terms of H2A, because then H2A would cancel out. So what we're going to do first is express these two terms in terms of H2A. So alpha, the fraction of H2A, I'm not going to do anything upstairs. I'm going to leave that alone, and I'm going to leave the first term downstairs alone. And now I'm going to substitute in something else for HA minus. I want to express it in terms of H2A, and I think I can use Ka1 to do that. Ha minus, wouldn't that be Ka1 times H2A divided by H plus? I'm going to write this expression here for Ha minus. And now I'm going to do the same thing for A minus 2. Let me rearrange Ka2 and solve for A minus 2. That still isn't quite there. Again, we wanted to express A minus 2 in terms of H2A, but we've only gotten it in terms of HA minus. What can we do? Well, we have an expression for HA minus. Maybe we could plug it into here. And what would that give? That would give Ka1 times Ka2 times H2A divided by H plus squared. So that was useful because all four terms in this equation have H2A in common and they can cancel out. So what does that give us? That gives upstairs just a 1, and downstairs this would be just a 1, and we would have Ka1 over H plus Ka1 times Ka2 over H plus squared. And maybe we should try to simplify this complex fraction. We could multiply by 1 in the form of H plus squared over H plus squared, and I think that ought to do it. The fraction of H2A would be H plus squared upstairs, and then downstairs, again, I'm multiplying all three terms by H plus squared. So H plus squared times 1 is just H plus squared. And then H plus squared times this term would be Ka1 times H plus. And then H plus squared times this term would just be Ka1 times Ka2. This is a useful equation for your extra credit assignment. When I made that fractional composition diagram, you can see part of it here. I had an Excel spreadsheet and I made a column for pH, and maybe I entered 1, 2, 3, all the way down to 14. And then I had a column for H plus. So I used Excel to get all of these concentrations. And then for alpha H2A, I typed in this equation that we just derived. You don't have to derive this equation. We already did it, and Harris gives it to you in the text. I just wanted you to see it. There are similar equations for the fraction of HA minus and A minus 2. The fraction of HA minus would be the same denominator that you see here, and notice how for the fraction of the fully protonated form, this first term is in the numerator. Well, which term do you think is going to be in the numerator for the fraction of the intermediate form? It'll be this second term, Ka1 times H plus, and then a very similar equation for the fraction of the unprotonated form. You'll have that same denominator. And then upstairs, you'll have this term, Ka1 times Ka2. So you do not have to derive these equations, but you will be using them for your extra credit assignment, which is, again, to make a plot of alpha as a function of pH for H2A, HA minus, and A minus 2. So I hope that helps you begin your extra credit assignment. Thanks for listening and good luck.